So as we talk about probability and statistics, it's helpful to keep the high level view of what we're doing. Big picture, statistics helps us make confident decisions with limited information. It's of course a discipline that involves analysis of data, just like the measurements that you're taking right now. And the key thing is that it's transformative. It takes that data, those measurements, converts it into some kind of quantified information, like a summary statistic, and that information can be used, can convert it into knowledge and used to make a decision. That's the fundamentals. That's why we're doing it. We're trying to improve our analysis. We often will, in the process of doing analysis with statistics, making decisions, we'll present data, we'll interpret data. That's all part of the discipline of statistics, Statistics 101. A statistic, not plural, is the actual quantity that's computed from whatever sample measurements or sample data you have. It might be an estimate of an important parameter. It might be a summary description of the data, like mean or standard deviation, or it might be some kind of hypothesis about analysis test, a criterion used for evaluating hypothesis. You have heard of many statistics and used them. Even count is a basic statistic. Mean, mode are also statistics. You often hear people talk about statistics and probability and statistics. They're not exactly the same thing. Probability concerns numerical description of how likely an event is to occur. So when we talked about the trash can fire, we're starting to talk about probability. We're starting to count how many times something occurs and then come up with an estimate for how likely that is to occur relative to the total number of times we're counting for. 0 is something is unlikely, low probability, or is no probability. 1 is absolute certainty. Probability ranges between 0 and 1, or you could think of it as 0 and 100%. And of course, a higher probability is associated with an event being more likely. There's Bayesian and frequentist views of this, but in general, we're talking about frequency and the frequency distribution of data, as evident like by bar charts that we call histograms when counting the frequency of data within a bin. Sometimes people use probability and confidence and likelihood different ways, all meaning different things, sometimes incorrectly meaning the same thing. Sometimes people use probability to relate to the degree of belief that an event will occur. We'll use probability distributions to assume how our data is distributed, typically using a Gaussian or normal curve. In general, when we're talking about probability, we're going to hit a lot of topics, but we're not really going to dive into theoretical topics. Mostly we're talking about measurement statistics, particularly that type of measurement statistics that are useful for decision-making in industry and the kind of jobs that you'll be in. I'd like to pose a discussion on statistics by starting out with an industry application. The application in this case, and it's a constructed application, a made up one, is that a national consumer electronics retailer has recognized that at-home installation of their flat screen televisions is a major customer satisfaction issue. The problem has led to higher than expected product return rates and profit loss. So rather than stock mounting hardware for its wide range of TVs, they're experimenting with a process to order, fabricate, and ship customized mounting brackets on demand using a mobile app and an automated fabrication facility, and then shipping of custom fabricated TV brackets like these ones right up here. These are custom fabricated brackets for televisions. To improve the customer satisfaction and profit, the custom fabricated mounting brackets need to arrive as fast as possible with the lowest cost for shipping. So a young engineer, she wants to make a data-driven decision and decides to take a sample of parts from the factory. We identify that shipping is a key parameter in this whole process. We'd like for shipping to be the appropriate type of shipping that's lowest cost and fastest to get to the customer. The young engineer identifies that product size and weight are key variables in shipping and seeks to take a sample of a bunch of brackets that were manufactured to see how length and weight relate and to see different attributes that can be quantified about length and weight of these brackets. She could use just design drawings and assumed densities and things like that, but it wants to have actual physical data from physical measurements in her sample. So she samples some brackets, 11 of them, and takes measurements of length and weight, inches and pounds. The data is summarized in a table here. In looking at this data from this sample of 11 brackets, there's some simple questions she might ask. How many samples? Well, she chose the samples, 11 samples. What numbers best describe this data? What's their range? What's the max, min? Is there a central tendency in the data? How do length and weight of the brackets relate? Are there any unusual measurements? These are the kind of questions that we can use statistics to answer. So some simple statistics, descriptive statistics is what they're often called, can be taken. Let's look specifically at the weight variable, the weight sample. There's 11, count of 11. The maximum weight, 10.84 pounds. Minimum weight, 4.26. The average is 7.5. And the standard deviation is 2.03. In the square of the standard deviation, the variance is 4.13. Those statistics give us a snapshot, a summary of the sample. We might also, for this particular application, want to know the relationship between these two variables, length and weight. And so, just like we've done with regression in a couple other labs, the relationship can be summarized by y equals mx plus b, y equals a1x plus a naught. And we simply find the slope and the intercept. Slope is 0.5 between length and weight, and the intercept is 3.0. R squared is a statistic that helps us measure how good our fit is, our model is to our data. R squared of 1 is a perfectly fit model to our data. 0 is a very poor fit, representing just random variation and no actual fit. And R squared of 0.9 is very good in engineering. And R squared of 1.0 is suspicious. Most likely you've done something wrong. You've overfit your data if you have an R squared of 1.0 and if you have a real measurement application. And R squared of 0.6 might be really good in social sciences where human behavior is a factor. R squared of 0.67, or about 0.7 in this case, indicates that there's a generally strong relationship that's linear between length and weight, but there's some noise in there. In this application, the engineer decides to take more samples. She had to use a tape measure and a scale to take the measurements. And she goes back on 4 different days and sets up the sample, takes the measurements again, and gets this table of results, all with 11 samples, 4 different cases, 4 different trials that were repeated. And she goes and repeats the same statistics for each of these additional trials. Those statistics for weight are summarized down here in this table. And there's some really interesting results, kind of some expected and some not expected. In this case, the average value of each of these trials is exactly the same, 7.50. The standard deviation and variance are exactly the same. And even the R squared is the same, with the same slope and intercepts for each of these trials. The only measurement statistics that are different are the maximum and minimum ranges. So that's an interesting result. Same exact statistics, same exact results for regression, average, standard deviation. So if she were to draw a conclusion about the repeatability of this test, it would indicate strong repeatability, that the results are very consistent or reproducible. So another thing that you do when you do statistics is not just crunch numbers, but you also visualize data. There's different ways to visualize data. You've done some of this already. You're going to do some histograms. You've already done some plots, rectangular, simple plots, scatter plots. And if you scatter plot these 4 different trials, this is the result that you get. You can see that the result shows a fairly decent linear trend upwards to the right between length and weight. And you can approximately fit that by a straight line, a linear regression trend line right through the middle. It's evident that there's some scatter in the data, which is not unheard of, and it's very common with any kind of measurement task, just like what you're doing today. But a little bit of a more close inspection of this data reveals a totally different story. If you take the 4 trials and you make 4 different plots tiling each trial, you see a totally different story in the plot. The first plot on the top left was our first sample, which shows a normal linear fit with some scatter around it, random error. But the second plot, top right, shows what's not a linear relationship at all. In fact, it would be better characterized by a quadratic equation or a parabola. In fact, it's definitely not linear, it's parabolic. And so a linear model would be a poor choice of trying to approximate that data, even though the numbers are exactly the same for something else. The window on the bottom left shows the third trial, and the third trial has an interesting result as well, which is that it has a strongly linear relationship at a slightly different slope, except for one key point. And that key point is an outlier. So even though the statistics tell the same story as all the other plots, all the other samples, clearly that outlier is driving that particular result. And if it were removed, the results would be entirely different. And lastly, the plot on the bottom right is just kind of nonsensical. It indicates that there's a test equipment issue in the 4th trial, that all of the X values are pretty much the same except for one. And even though they're the same, there's just random noise in the output Y, the weight, that doesn't make much sense at all. Almost certainly the tape measure or the scale has a problem, even though there's one single outlier driving the numbers to look exactly like the others. So this constructed example is actually known as Anscombe's quartet. And Anscombe's quartet helps us make a few key points about statistics. The first is that simple statistics can help us understand our data. We just did mean, standard deviation, max, min. It's really, really simple statistics. But a key point is that statistics alone can be misleading. In fact, it's easy to lie with statistics. Just because we put a number to something doesn't mean that we believe it. Doesn't mean that it results in a causal relationship between some thing and some other thing. In fact, there's a book that used to be given to all government employees called How to Lie with Statistics. And the point of the book, How to Lie with Statistics, was to be cautionary, to say, don't do this. But of course, somebody in the media heard that everybody in the government was being given this book called How to Lie with Statistics, and they banned it. So government employees can't be given a book with that title, even though the point was a good one, teaching people that you shouldn't be misleading with statistics. If you don't think that statistics can be misleading, watch your television or your internet channels for 15 minutes. You'll see advertisements for all sorts of crazy health stuff that's going to solve all of your medical problems. If you eat Cheerios, did you know you're going to reduce your risk of heart disease? 9 out of 10 doctors said that. Nah, that's probably not a true story when you go back and look at the real data. I'm sure there was a real study, probably sponsored by a prestigious organization, but real doctors wouldn't make real conclusions like that unless they were paid to. Maybe there was some correlation, but causation, maybe not. So one surefire way to improve your use of statistics and improve your interpretation of data for decision making is to visualize the data. Visualizing the data with simple plots, scatter plots, histogram, bar charts, even pie charts, which are not my favorite, can help with analyzing data, telling the true story of what's going on with your data, with your numbers, using statistics and visualization so you can make better decisions. We have a lot of concepts, terminology to discuss when we talk about statistics. The population is all possible values of a measured variable. Think about a box of bearings that you fabricated in your shop, and you need to do some quality control checks on, some process control. There's probably 1,000 bearings in a box. And a normal strategy would say, we don't need to measure every single one. We're just going to take a sample, maybe measure 10 of them to check our quality of our process. So sampling, that's the process of obtaining data through repeated measurements of a variable under fixed operating conditions. It's also the process we describe for extracting sample measurements from a population. A measurand is the measured variable being sampled. Sample is the possible subset of values taken from a population. In our lab today, we're going to assume that the population is all of the measurements taken from all the students in your section. So we're going to assume population behavior, that we have a defined population. It might be about 36 measurements, 36 parts. In practice, not all populations are exactly measurable. It's difficult to exactly know how many people are in a country or in a town. You might see Wikipedia that says there's 3,000 people in Potsdam. That might not be an exact number. It's hard to quantify that. Even more practically, if you had to do something like measure the length or geometry of fish in a lake, you can certainly see that it's impossible to get the entire population. The only way to get the entire population would be to drain the lake and kill all the fish, and that would be entirely counterproductive. So what we do is we fish. Fishing is like sampling. The next chapter after probability and statistics is error. And error is a key thing that we're going to learn how to do in this class, how to calculate and estimate error. Errors themselves are the difference between measured values and true or actual values. A key idea here is that we are assuming a true value, that there is a true value. And in fact, for your measurement parts, if you can measure it accurately enough, there is a single true value in there. But often we see random error. Random error is manifest through data scatter, limitations of a finite sample. Those lead to limitations in how we can predict the behavior of the population with certainty. There's random error. There's also systematic error. Systematic error is characterized by an offset between the true or known value and the average value in our data. If we can identify a systematic error, we usually can correct for it. So for instance, if you don't zero your instruments and all of your instruments are off by a certain fixed value, you can just correct for it. You can offset your data. So in probability and statistics analysis in this chapter, in this week, we're going to assume that systematic errors are not relevant, and we're going to assume the average error, random error, is 0. We're going to assume that the true value is our mean population measured value. So the fundamental problem that we have in measurement statistics is to estimate the true value, which we call X prime in our notation, with the most probable estimate. We call that X bar, based on available data with an uncertainty interval, U sub X bar, at some probability level P%. Uncertainties are the numbers that quantify the possible range of effects of errors. They're not the errors themselves. If we knew them exactly, we wouldn't call them uncertain. They are uncertain. And the only reason that we have confidence in our uncertainty analysis is that we all agree on the same methodology. We're using it and reporting it. So we don't know the errors at all. We estimate them with uncertainty analysis. More on that in chapter 5 next week. A few more key concepts and definitions. A random variable is just a variable subject to the effects of random variation. Not all variables are random. There are certain things that are deterministic. If I ask you to do some statistics on schools, a deterministic variable might be the type of school: elementary, middle, high school, college. It's not a random variable at all. It's just a deterministic value. In that case, a categorical value. But we are often dealing with random variables in our measurement applications in this class. And those random variables tend to have a central tendency, some value about which all other values are scattered. As I said before, probability deals with the concept that certain values of a variable may be measured more frequently relative to others. Probability deals with how likely an event is to occur between 0 and 100%. Probability density describes the frequency with which a measured variable assumes a particular value or an interval of values. We can determine the central value and those scattered around it from probability density functions that we can measure from assumptions of the way our data is shaped, for example, Gaussian. Before we get to probability density functions, with discrete measured data, the simplest thing that we do to start to look at the idea of a distribution is we compute a histogram and plot a histogram. A histogram is just a count of the number of measurements along a number line within certain intervals or bins. We count up, we tally up the frequency or the count of those measurements within bins, equal width bins, and we draw them. That's a histogram. The Bindant rule establishes a correlation for how many intervals you should expect for a given histogram based on sample size, with the idea that you want, in general, to have each bin to have at least 5 measurements in it, depending on your data. You're going to be tasked with making some histograms. And one of the things that's a little bit of my pet peeve of Google Sheets and Excel is that they're not very good at making histograms. And in fact, they have some algorithms for choosing the structure of a histogram that don't really report data the way we normally like to see it, but it's generally what we have and what we're going to use. You might find better histogram functions in MATLAB, the hist function. If we have a continuous variable x, we can take the limit as a small value delta x goes to 0 of that frequency, and that becomes a probability density function. It's a statistical model of the population of a variable in the limit that n, the sample size, goes to infinity and delta x goes to 0. We sometimes call it a PDF. We're generally assuming normal Gaussian distributions. There are others. Generally, the central tendency of a PDF yields the desired representative value that gives our best estimate of the true value or expected value of our data. Normal function, bell curve like, it's not the only one that we're interested in. Log normal is another distribution like this. We might see uniform or rectangular distributions, particularly when we assume a process is totally random. We might have some reason to use triangular distributions or Poisson distributions. For Poisson distributions, randomly occurring in time or space with a parameter lambda defining the probability density function. Or we might also use a binomial distribution in the appropriate case shown here. Definition of population true mean is shown here using a t variable and also an x variable. X prime, the true mean, is the limit, or I'm sorry, the integral from minus infinity to infinity of x, the random variable, times p of x, the probability density function of that variable, integrated over dx. For discrete intervals, the mean is just the sum of the values divided by n in the limit that n goes to infinity. While mean describes the central tendency, variance and standard deviation describe how the data is spread, how it varies about the mean. Higher variation, higher variance and standard deviation indicates a process that's more spread out than one that has a strongly centered value with a low standard deviation and variance. Generally, we like to have low standard deviation, low variance in our measurements. How do we define it? We take each measurement value, subtract off the mean, square it, and integrate over the domain. Sigma squared, the variance, in particular, is the integral from minus infinity to infinity of that deviation, x minus x prime, the mean, squared times the probability density function, integrated over dx. And of course, the standard deviation is just the square root of the variance. When we square root the variance, we get the units the same as the mean, which is convenient. When we describe the population behavior, in this class, we're, as I said before, often using this Gaussian relationship. It's shown here with two parameters, x prime, the mean, and sigma, the standard deviation, where the definition of the probability density function for a Gaussian distribution is 1 over sigma over square root of 2 pi with an exponent e to the minus 1/2 x minus x prime squared over sigma squared. These are assumed true variance and mean values from the population. Notice that the maximum probability occurs at the central value, the mean value. The shape of the curve, as defined by this distribution, can have long tails, short tails, be narrow or wide, depending on the process. With that Gaussian curve, the normal curve, we often transform mean and standard deviation variables to a standardized form called the standardized normal variate, or Z value, the Z statistic. Actually, it's not a statistic, the Z, Z statistic is fair enough to say, or Z score sometimes is what it's called, where we take an X value, subtract off the mean, and divide by the standard deviation. That scales your distribution so that it's centered on 0. And because the Gaussian or normal curve is symmetric, we can compute the integral and tabulate it using a normal error function that is integrating from 0 to Z1, half of that curve, and then just multiply times 2 to get our probability values. That's summarized in table 4.3. 4.3 we'll use a lot in the assignment. It characterizes the one-sided integral solution for the probability given a Z value. The Z value being the difference between the mean and the value you're measuring over the standard deviation. You use this table to define a precision interval or to define a probability. You're certainly familiar with the idea that standard deviation describes how varied a process is. In process control in industry, you often hear of 6 sigma, and there's a lot of actual methodology around 6 sigma, but the name comes from the idea of your data being within 3 standard deviations of the mean, 3 sigma. 99.73% of the area under the curve of the probability density function will be within 3 standard deviations, plus or minus. 95.45 will be within 2 standard deviations, and 68.26% of the data will fall within 1 standard deviation. And that talk was all about populations. But in the reality, we have finite sized samples in most of what we do. And so we have to have slightly different statistics when we're making inferences about a population from a finite sized sample. The mean definition is pretty much the same, 1 over n times the sum of the values x, and the variance is also the value x minus the mean squared and summed up. But instead of dividing by n, we're dividing by n minus 1 for a sample. We lose a degree of freedom is what it's called. But the standard deviation is also just the square root of the sample standard deviation is just the square root of the sample variance. When we talk about sampling or finite statistics, it's really important to understand that it's essential that we try to find an unbiased sample. We'd like to make sure that the random sample doesn't systematically differ from the population from which it was drawn. With a sample, it's impossible to know every possible thing you want to know. So there's a compromise with a sample. You'd like for each of your samples drawn to be independent of the others. So you'd like for them to be equally likely to have occurred in generating an unbiased sample. Generally, we use a random function generator like RAND as a function in Excel or Google Sheets. Generate a random number and then sort it and pick from that for a random sample. You might also have some other blind process drawing out of a bag or something like that for random selection. There are some times where we use sampling that's not entirely random. For example, stratified sampling. If I go back to looking at average grades for kids in school, I might want to stratify my sample across elementary school, middle school, high school, college, to have a more fair estimate, a more representative sample. Or if I'm drawing from a population where there's differences in the number of occurrences of a particular categorical variable, I might choose to stratify my data so that I get a fair representation from the things that I'm interested in sampling. Maybe in engineering, there's maybe less of a certain type of student than another student, and we have to stratify across our sample across that particular categorical variable. So of course, with a sample, generally, the larger the n, the larger the sample size, the more confidence we have in our conclusion based on our statistics, but only if that sample is random. Definition of mean value. Most common is the arithmetic mean, summing the values, dividing by n. The choice of the type of mean we use depends on what we're doing. If we're racking and stacking a bunch of variables for a ranking type exercise, we might use a mean other than the arithmetic mean. We might use something like a geometric mean. A geometric mean is a product of our x values taken to the nth root. If you use a product and you have a value like 0 or 100, if you're ranking percentiles, that can drive results to the extreme value one way or another. It's a different way of looking at how our data clumps together. With our population, we assumed a Gaussian distribution in general. But when we have a finite number of samples, we need to make a little correction for that Gaussian probability density function. And that's, we use the student's t distribution. Similar definition to x, similar definition to z, but the t variable is the sample mean minus the true mean over the standard deviation divided by the square root of n. For higher n, our t value, which is kind of a coverage factor or a correction factor, makes it so our probability density function is closer and closer to normal or Gaussian for higher n. For lower n, lower samples, we have a bigger correction factor or coverage factor t that's used to define a precision interval. We can say for our measurement that we can have t, student t, for a given number of samples and assumed probability times the standard deviation as a plus or minus precision interval about a sample mean. And we can say that with a certain probability, such as 95% probability. When we use students' t distribution, we usually have it tabularized. In our case, we have it tabularized in table 4.4, where we have, instead of n, we have a new variable nu called the degrees of freedom, which in this case is n minus 1, the number of samples minus 1, tabularizing the student's t value for 50, 90, 95, and 99% probability. As nu goes to infinity, these numbers draw closer and closer to the same values that were in the z table. If we're to take additional measurements from additional batches, how do we quantify how good our estimate is for the true mean based on the sample means. We can use variation in the sample statistics gathered from each different data set, each repeated batch data set, to characterize our normal distribution about the mean. And we can assume that the variation is estimated as the standard deviation of the means. This statistic, called the standard error, is one of the most important statistics in measurement statistics. The standard error, S sub x bar, is just the standard deviation divided by the square root of n. Standard error provides a measure of how well our measured mean value from a small sample size represents the true mean from the entire population. So we can estimate the true mean x prime with x bar plus or minus students t times S of x bar. That helps us establish, for a given probability, a confidence interval as a quantified measure of random error in estimating a true value of a mean. So plus or minus t times standard error, S of x bar, represents the random uncertainty in a mean value at p% confidence due to variation in the measured data. It's very common for you to have to provide a confidence interval. If you ever see confidence interval, remember to use the standard error, standard deviation divided by square root of n, in your analysis. We're section 21 today, one of 6 sections, each doing the same thing. 6 different sections represent 6 different repeated tests, or 6 different pooled tests is what we're calling it. And we have some slightly different statistics for things like mean, variance, and standard deviation based on pooled data, like as drawn from 6 different sections. Those 6 different sections or pools might have different numbers of students in them, 25, 30, 35 in different classes. And so when we pool statistics, we weight each value by the number of measurements from each pool. We can also calculate a pooled standard error, similar to standard error, but also weighted by the number of samples from each pool, M. And then we can also calculate something called a mean square value, which is a statistic that can test for significance of variation between means, as defined here. S x squared b sub b. We can use that with an F statistic to test the equality of the population means under a null hypothesis. And we can also test the equivalence between 2 mean values of repeated tests using a T statistic as defined here. One of the last assignment problems for you all is computing the pooled statistics, F statistics, and T statistics for other classes, for other sections. If you recall in middle school doing a science fair project, you probably were asked to state a hypothesis. So simply put, a hypothesis is a statement that something is believed to be true. But real hypothesis testing uses the tools of statistics. We define a default or a null hypothesis. And our null hypothesis generally is that the difference between some measured value of a population and an assumed behavior is small enough to be considered as due to random chance alone or random variations alone. That's a null hypothesis. And then we might evaluate some alternative hypothesis. For example, the difference between the observations and the expected behavior in our results is from something other than random variation. Maybe a systematic effect. Maybe we find that everybody has a result for a measurement that's off systematically. Alternative hypothesis. The method of hypothesis testing, 4 simple steps. We establish the null hypothesis, H naught. Generally, that the true value is some value X naught. X naught is the population or target value. And then we establish an appropriate alternative hypothesis, H sub A. We assign a level of significance alpha to determine the critical values that set a, quote, rejection region. And then we calculate the observed values of whatever our test statistic is, which depends on the application. And we compare our test statistic to our threshold or our critical values. Generally, those are going to be on one side of a distribution like as shown here. If the observed statistic is in the rejection region, of course, then we reject the null hypothesis. Otherwise, we do not reject. And those are the words we use with formal hypothesis testing: reject or do not reject, which is not the same thing as saying this is the cause. We're just saying this is not the cause. It's a different way of saying something, and it's important to make sure that we use that kind of terminology with hypothesis testing. Some examples shown here for different types of tests. Similar to the standard error, if we have a bunch of repeated samples, repeated tests, we might not just look at the variation in the means, we might look at the variation in the variance, the standard deviation, okay, or variance. We might like to see how consistent our standard deviation is, how well our test sample variance matches our predicted population variance. We use a chi-squared for that with an alpha significance level, and a distribution for various degrees of freedom nu is shown here for typical chi-squared plotting standard deviation. Regression analysis. We also use the words least squares to describe most of the regression modeling that we do, because we're attempting to minimize the sum of squared errors between the actual data and some model. Often in our case, we're using a linear model, or we've used log linear models or log models. They don't have to be that form. They can be other forms. They could be polynomial regression or any other form that we want. We could use neural network based type forms, generally minimizing some objective function related to minimizing squared error, these squares. Generally, the point is that we're trying to model the functional relationship between two variables. Sometimes we call it the dependent and independent variables, or the target variable and the features. And we've done that in the past with the moisture calibration, length transducer, temperature probe, time constants. A key statistic for regression is not just R squared, but also standard error of the fit. Standard error of the fit is each value of the output or the target value minus the modeled target value squared divided by degrees of freedom and square rooted. Just like we do confidence intervals for individual measurements, we can do confidence intervals for a regression model, where we take students T times our standard error of the fit as the basic confidence interval. If we account for variation in X, we can refine that confidence interval using a Sheff band that is not fixed along X, but changes as a function of X with the equation shown here. R squared is the performance statistic that we often use. It's not the only one. You might hear of something else, Bonferrion information criterion, or a Keiki information criterion, or other measures depending on the model. Area under the curve is another example, or of an ROC application. R squared, the ratio of the sum of squared residuals over the total sum of squared error, which is to say the y values minus the curve squared summed up over the y values minus the average y value squared and summed up. R squared is not the same thing as lowercase r, which is generally the correlation between two variables. Don't be confused by that. We do sometimes look at correlation between variables, depending on the analysis that we're looking at. And one thing to consider is if you're building a regression model, you'd like for your variables to be, your features X to be independent of one another. If they're not, that might affect how you perform the regression analysis. A couple other statistics that are used are the standard error of the intercept and standard error of the slope. And you can compute those from the linest function in Excel or Google Sheets. When you look at the data for our results, you're going to find that there's some numbers that just don't make sense, or that they're just more extreme than other values in our sample. You might have some suspicion that those are mistaken data points. Maybe they're outliers or anomalies, spurious cases. So there's methods to identify and remove anomalies, to identify and remove outliers. One method is simply just to look at anything that's outside of 3 standard deviations as a potential outlier. Another is Chevanon's criteria, which looks at the Z probability being less than 1/2 divided by the number of samples as a criterion for identifying an unlikely to occur event or unlikely to occur measurement. So we'll do that in our analysis in our class. We'll identify anomalies and try to remove them. We can do that in more than one stage. The first time you pass through and remove an anomaly using this criterion, you'll then want to go back and look at your data a second pass, maybe even a third pass, to identify outliers. An initial extreme value, which is maybe like a super anomaly, you can take that out, but you then might find that you still have some values in your measurements that are more subtle outliers, more subtle extreme values. The big challenge with outliers is deciding what to do with them. Do you remove them from your analysis or not? It's really important to note that most of the findings in science occurred by some kind of spurious or unusual or unexpected result. In other words, when somebody said that doesn't make sense or aha, that might have been considered an outlier in one sense, but maybe that was the real interesting thing in another sense. The thing that actually spurred on some deeper investigation into something that we learned about. So don't discount pesky cases just because you have learned how to use outlier detection. That might be the real interesting result after all. A common task for an engineer is to decide how many measurements you need to get a certain confidence interval. There's an iterative method to do that, shown here. Assume a confidence interval, divide by 2, we call that D, and that equals students T times the standard deviation over square root of N. The trick with this little relation is that students T is a function of N, so you have to guess a number of measurements first and check to see if this relation holds. If it does, then you've got about the right measurements that you need to get a certain confidence interval. If it doesn't, then you just try a different N until you get those numbers to equal, and that should tell you how many measurements are required. In our assignment, I've asked for you to give me the number of measurements required to get a very small confidence interval, 0.001 inches, 1,000th of an inch, for one of the measurements you're taking. What I expect for you to find is that the number n is going to be so big that it's going to be impractical to actually get that confidence interval. So the rest of this last few minutes is just going to take a look at some example problems. I call this a tutorial. These are textbook problems and their solutions, essentially example problems from the text that walk you through how to do common statistical analysis tasks. Most of these questions are related to the assignment that you have. And for each of the assignment questions, I've actually given a reference in the assignment to say which problem in the example slides relates to that particular question. So example problem 4.23 asks you to determine the range of values for various bracket hole diameters containing 70% of the population of each measurement using the normal error function and assumed population mean and standard deviation from your section's data. That's comparable to question 2A, slide 2A and 2B, which just shows you how to take that probability and use it relative to a z-table. Since a z-table is one-tailed, you need to half that probability. 70% becomes 35%. And you look up in the z-table where you find 35%. It happens to be at a z-value of 1.04. Once you know that z-value and you have a known population mean and standard deviation, you can go back and find the limits for a range of values with a 70% probability for your measurement data. Problem 4.24 asks about pump shaft length L1, asking what's the probability that L1 exceeds 1.38 inches during any measurement. Again, using a z-score. And that relates to example problem 3A, which asks a similar question for a compressor. At a fixed operating setting, the pressure in a line downstream of a reciprocating compressor is known to maintain a mean value of 12 bars and a standard deviation of 1 bar based on history. What's the probability that the line pressure exceeds 13 bars during any measurement? Well, you compute a z-score, you look it up in the z-table, and then how do you use that probability? Well, the question asks for what's the probability greater than a certain value. So you subtract off 1 or 100% from that measured p-value, probability value, and that gives you that there's a 16% probability of a measurement exceeding 13 bars. When you use a z-table for a question like this, it's important to note whether or not the value that you're evaluating is on the left or right side of the mean. If there's outliers in our data, we might find that our measurement is over here on this side, and that we need to change how we approach using the z-table probability accordingly. Problem 4.25 says take n equal 10 samples from pump shaft length L2. Compute the sample mean, standard deviation, and then assume a true population mean from all the data from our class. And then estimate the probability of getting your sampled results due to random chance alone. This corresponds to example problem 4, where again we use a z-value and we compute our probability. The example probability shown here is about whether a student conducting an experiment to determine the value of the gravitational constant got his result by chance. His result was 9.5 meters per second squared with a 0.1 standard deviation. But we know the true value is 9.8. In this analysis, assuming a normal curve, the probability of getting that result of 9.5 meters per second squared for the gravitational constant is very small. So it's very likely a systematic error, a mistake in the experiment that led to a result like that. Your result is not likely to be such a small probability based on the question I've asked. Another question, 4.26 relates to slide problems 5.8, 5A and 5B. Also for measurement L2 from the pump shaft, estimate the expected range for 95% of the measurements using a T distribution. So now we're switching over to looking up students T for given degrees of freedom, multiply that times the standard deviation, and that gives us our precision interval with 95% probability. Couple more problems in here. They all relate, most of them relate to slide problems. I'm not going to go through them in detail now. I will say that as we close up shop here, I'd like for you to gather your instruments and gather your parts and bring them back up front. The brackets and the pump shafts go on the right side of this toolbox, and then all the other instruments go in the toolbox over here. I'm planning to leave this toolbox unlocked so that y'all can complete this this exercise. As I said before, no one's allowed to take any of these instruments out of lab. You got to do any work on these measurements here in lab, and please get these measurements finished up promptly and reported in the spreadsheet promptly so that others can continue on their analysis.
A bunch of people are asking about
QR code, I'll pull up the QR code one more time.
the graphics and stuff going on.
Check.